previously when we have Fermat's-Slater theorem. But then when we are doing modulo p to the power of k, because we know, because from our lemma just now that this is p to the power of k minus 1, p minus 1 is congruent to 1 modulo pk. So we can just get back the same result here. The proof is basically completely similar to this one, so you can just refer to this. So I won't write out the proof, but it's basically that, right? So we have this result. And a good example, suppose now I want to find 3 to the power 3 to the power of 6 to the power of 1000 modulo 81. And then 81 can be written as 3 to the power of 4. So this is 3 to the power of 4. So 81 is 3 to the power of 4. So p to the power of k minus 1 times p minus 1 would be 3 to the power of 3 multiplied by 2. So 3 minus 1 is 2, and then 3 to the power of 3. So 6 to the power of 1000 modulo this 3 to the power of 3 multiplied by 2 will always become 0. Why? Because 6 to the power of 1000 can be rewritten as 2 times 3 to the power of 1000. And then you can just like see that this thing will always be able to, when you divide this with that, then you always like get the remainder is always 0. So you get that 3 to the power of 6 to the 1000, 3 to the power of 6 to the power of 1000 modulo 81 is congruent to 1. Yeah. Okay. So for composite modulus, just now we look at prime power. Now let's just look at composite modulus. So but before that, I have to recap on Chinese remainder theorem, which what we have said previously. So this thing is it's basically like a immediate result from Chinese remainder theorem. So we write n to be p to the power of k1 and p2 to multiply k2. So this is just factorization, prime factorization of numbers. Then what I'm claiming here is that there's a one-to-one correspondence between x, this x mod n. So x is just an arbitrary value, and the solution to the system of modular equation x prime. So what I'm saying here is that suppose x prime is a solution to this set of equation. And what I'm saying is that, so what I want to show is that x is basically x prime. So why is this the case? It's because from the uniqueness of Chinese remainder theorem, firstly we see that x will certainly satisfy all this equation because the right hand side is just x. So if you plug x in x prime, this will always become the solution. So x will always satisfy the solution, right? So from the uniqueness of Chinese remainder theorem, x prime is exactly equals to x. So all the solutions for this will be exactly equals to x. Basically saying that there's a one-to-one correspondence between x and the solution to this. So this is sort of like a bijective mapping between them. So if you have a solution here, then you can map it to this. And if you have this, then you can map it as a solution to this set of equation. So why do we need this? It's because we need to prove Euler's theorem. Okay, so Euler's theorem is like our final theorem for the required for RSA. We write n. Suppose my modulus is not prime power. My modulus is some composite number. So I write my composite number as products of prime powers. So this is factorization. Then I define this phi of n. So this is called this symbol called phi is called phi. So I define this as phi of n as this thing. Okay. So basically you just take all the prime factors, and then the power is k1 minus, oh okay, sorry, this should be p1. This is a typo. Okay, yeah. So yeah, so you just take that. You just take p1 k minus 1 to the power of all the things, and then you multiply by P1 minus 1, and then P2, K2 minus 1, and then you multiply by P2 minus 1, and so on. So the claim is that this, when you raise x to phi of n, it will be equivalent to 1 mod n. So this very arbitrary looking thing, actually you can see some sort of like relation on why do we even choose phi to be this, right? It's because we see that p to the power of k minus 1 and p minus 1, this thing is somehow related when you have pk. So if you define phi n to be something like that, then that would probably give you something good. So that's what I'm trying to say. Okay, so let's see what's going on here. Oh, this is also wrong. This is so wrong. Okay, so this part is very wrong. Okay, yeah, this part is very wrong. Okay, then I'll just rewrite. Okay, so let's look at the proof. Because there is a one-to-one correspondence between x and the solution of this, so we can rewrite this in terms of I try to find solution of x prime to this equation. So what is x phi n modulo p1 k1? Because phi n is a power of all these things, so this is just saying that this is p1 k1 minus 1 p1 minus 1 multiply with a lot of things, right? Because we define phi n as something like that, right? And then in the end we have modulo p1 k1. And just now we already see that the first term here will result in 0. Sorry, will result in 1. So this will become 1 to phi n divide by p1 k1 minus 1 and then p1 minus 1. And then 1 raised to any power is equals to 1. So we have that x to the phi n in every equation will become 1. It will be congruent to 1. And just now we say that so by uniqueness of Chinese remainder theorem, we know that 1 is a solution to this set of equation. And then just now, because we also mentioned about the one-to-one correspondence of all this, so we have that x to the power of phi n is exactly equals to 1. And which is also the solution to the set of equations. So any questions on this part? Okay, sorry for the typo here. Okay, right, just confirming everyone's okay with this. You can ask any questions if you have. Just type in the chat. Okay. Yeah, right. So basically we prove Euler's theorem. It's getting kind of messy. So let me just erase some of the not so important part. Okay. So we prove so we basically say that we have this value phi of n, and then when we raise x to phi of n, it will be equivalent. It will be congruent to 1 mod n. And we get a result for composite. So previously for Fermat's little theorem, we have that x to p minus 1 is congruent to 1 mod p. And then we have that when we are doing mod to the prime power, we have that x to the power of pk minus 1, p minus 1 is congruent to this. And then for a general integer n, this is what we have, which is the phi n. And it is basically just all the things multiplied together. So a simple corollary that we can get is that it's the same result that we had previously. So it's exactly the same as this. So for every x, right, if you raise to the power of d, you can always do modulo phi n, and then this will always get back, give you the original thing. And the proof is the same as how we have previously. Also, I want to note that phi n is looks very arbitrary, but it actually is called it has a name. It's called Euler's total function, and it's also the number of positive integers less than n that is co-prime to n. So that is just a remark, and you can prove this also. Similarly, using Chinese remainder theorem. So an application of Euler's theorem is that, let's say if we have 3 to the power of this thing, then what is the phi n of 35? So 35 can be written as 7 times 5. So the phi of 35 will be 6 times 4. Because 7 minus 1 and 5 minus 1. So this is modulo 24. And this whole thing, modulo 24, is equals to 3 to the power of 11, and this is 12. So a slightly non-trivial example that we have here is, let's say if we want to find d, such that for all integer x, we want to find a d when such that when x to the power of 7, I raise to d, I will get back x. So it means that x to the power of 7 is some element. So I want to map it back to x by raising it to power d. So I hope that when I raise it to power d, I can get it back to x. So is that possible? And from Euler's theorem, it says that it is possible. So how do we find this d? From the corollary 8.6, we have that x to the 7d is equivalent to x to the 7d modulo 24. And then you just solve the modular equation here. We have that d is basically 7 inverse modulo 24, and 7 inverse modulo 24 is just 7. So we have d to the d is equals to 7. So that means that whatever I do, right, whatever x I put in, if I raise to 7 of x to the power of 7, then this will always give me back to 1. Yeah, and this will be somewhat important when we talk about RSA later on. So yeah, that is the end of Euler's theorem. Any questions? Okay. Yeah. Okay. Then now we can finally talk about RSA. Yeah. You see, right? I have like 19 pages for all this. There's no more page after this. I have like 19 pages of I have 18 pages talking about math, and then 1 page talks about RSA. And then the title of this is called Number Theory for RSA. But we'll see that with all the theorems in mind, right, RSA becomes very trivial to understand. So RSA is a public key crypto system. It is introduced by Rivest, Charmé, and Edelman. So it is basically described in by three algorithms. We have setup, encrypt, and decrypt, and a security parameter lambda. So this security parameter is like probably, if you want to say, like 512 bits, and then or like 256 bits. It is related to that. So the setup for RSA is pretty simple. The secret key is PQ, D, and phi n. PQ are primes of lambda bits. N is P times Q. Phi n is the Euler total function, which I mentioned just now. So E is another chosen is a chosen prime number larger than 2, usually 65537. And D is an integer that satisfies this equation. So encrypt is just okay. So the public parameters is this thing. So this is the public parameter, and then the private parameter is this PQD and then phi of n. So to do encryption, we takes in the public key. It takes in the public key and the message. Then we raise m to the power of e modulo n. For decryption, we get the private key. We get the ciphertext and the private key. Then we raise the ciphertext to the power of d, and we get m prime. So now we want to prove the correctness of RSA. To prove correctness, we show that the decryption of an encryption gives us the original message. So basically, what I want to show is that this thing will be equals to m, because after I perform encrypt, so this is the encrypt function. After I perform the encrypt function, if I do the decryption on the encrypted message, then I should get back the original message. So plugging in the values, the encrypt of PKM is just m to the power of e modulo n, and then the decrypt is this thing raised to the power of e, just following the definition. So we have that m to the power of ed modulo n, and this is just that. And because we know that by Euler's theorem and the corollary that we have, this we can just write it as ed modulo phi of n, and ed is defined to be 1 modulo phi of n. So because ed is 1 modulo phi of n, this is m to the power of n, so we get back m. So this shows that the algorithm is correct when m is less than n. So now let's talk about the security of RSA. For RSA, the security of RSA relies on RSA assumption. So the RSA assumption is that given a message m, given NEC as per the description of RSA crypto system, it is hard to recover m. So by hard here, we means there is no polynomial time algorithm to recover m, because you can always brute force, right? You can always just run through all the possible numbers, you can always just run through all the possible messages and check whether it maps to C. So the RSA assumption says that it is hard to recover this, and yeah, so it is believed to be true. Okay, it is believed to be true, but it has been shown in a lot of special cases, special instances, that RSA assumption is not true. So, which is why we have a lot of attacks on RSA. So why is that the case? Mainly because that RSA assumption is just an assumption, right? It is not. It is never proven that this is hard. It is just assumed to be hard. So the thing is, so okay, now I want to make a remark is that suppose if we know the factorization of n, which is p and q, then we can compute d easily to recover the message m, because d is just e to the ed congruent to 1 modulo phi n. So d is just e inverse modulo phi n, and then phi n is p minus 1 multiplied by q minus 1. So if we have p and q, we can compute phi n easily, and then we can compute d easily. With d, we can decrypt the whole message. So suppose we know the factorization of n, then we can easily compute d to recover the message. So we have a conclusion that integer factorization problem is harder than RSA assumption. So this means that if you can solve integer factorization fast, then this implies that you can break RSA. But if you can break RSA, it doesn't mean that you can solve integer factorization fast. So So this thing, so this red arrow, which says that you can break RSA, means that you can solve integer factorization fast, is not proven. And the RSA assumption says that it is as hard as integer factorization. So yeah, keep in mind that all of these are just assumptions. So it is very likely that it is not very likely. Like it's possible that in the future we can find some algorithms to break RSA. Right, and so yeah, so the best known algorithm to factorize a number is general field safe algorithm, which has a sub exponential runtime of all this. But yeah, so yeah, even if RSA assumption is easy, integer factorization could still be hard. So now let's end the section of RSA with one simple example. So suppose n is 35 and e is 7. So just now we have shown that d is e to the inverse and this is just 7. The phi n is 24. Then if you want to encrypt n is equals to 23, then we just raise 23 to the power of 7, and then we get that this is 2. And then we want to decrypt it, we just raise 2 to the power of 7, and then we get that this is 23. Okay, so that sums up RSA. Right, and it seems very easy. Okay, not easy, but it seems very okay, it seems hard. Okay, it seems hard to come up with this kind of construction. Like you think about it as from a person who designed a crypto system. Like, so how would you come up with like something like RSA? So in fact, like if you want to come up with some public key encryption system, you need to have something like a trapdoor. So a trapdoor is basically that a function that you can compute. So you can a function that can compute fx easily, but cannot recover x easily. But given a trapdoor T, which is in the case of RSA, this is just an integer factorization. You can compute the inverse easily. You can find x easily. So there are not a lot of known trapdoors out there in cryptography. Maybe before I talk more about this, okay. So any questions on RSA, or just the sharing so far, from the beginning to the end, from the first part to the last to this last part. Cryptography is not just about trapdoor function. Trapdoor function is used by public key cryptography. So for symmetric key cryptography, it doesn't require trapdoor functions. It only requires one-way functions. But trapdoor function is stronger thing that is harder. It's a harder thing to get. Like it's not easy to find the trapdoor functions. And if you have trapdoor function, then it. So we haven't really found any trapdoor function that is proved to be hard. So we only found things that is assumed to be hard. We only find like possible trapdoor candidates that is assumed to be hard. For example, this RSA. But we haven't found any trapdoor that is proven to be hard. And later I'll show a wiki page on this. Okay, so okay. Maybe I'll just show it now. Okay, so yeah, if you look at the wiki page of trapdoor functions, we have these two, which is the RSA assumption and Rabin's quadratic residue assumption. So the RSA assumption only is like the RSA assumption is just like it's not it is just an assumption. But then Rabin's quadratic residue assumption actually says that if you can break this, then you can factorize integer very easily. But for RSA assumptions, even if you can break RSA, you cannot find integer factor. You cannot solve integer factorization. So in some sense, this is a stronger assumption because if you can break this, you can factorize integer. But if you can break RSA, it doesn't mean that you can factorize integer. And there's also a lot of candidates for trapdoor function. For example, one of the possible candidate is like the lattice reductions. Actually not lattice reduction, but the shortest vector problem. So the shortest vector problem is also a candidate for trapdoor function, which is basically saying that I have a short vector and then I want to like hide something, yeah. But I will not go too deep into this because this has a lot of technical details. So shortest vector problem is one of the possible candidate for trapdoor functions. And I think yeah, I think only these few. Like there's not much candidate for trapdoor functions out there. Yeah. So these are very significant. Yeah, and this is believed to be post-quantum secure for now. But yeah, it is only believed to be that. Okay, so maybe now I'll talk about the exercise. Okay. Let me share my screen. Okay, so we have a lot of, I think I didn't add new one because I feel that the end of this sharing basically says that you can do all the RSA down here already. So you have enough exercise from the beginning category. But I think there are some interesting ones that I want to talk about. For complexity one, I believe most of you all get it, which is this is just ON. Because you just recurse it down, and then you just count the tree of recursions down. So this one is slightly more complicated, but if you analyze it hard enough, then you can also get the answer. I think yeah, most of you all get it also. So okay, maybe I should ask which question should I discuss? Like which one do you want to know the solution to? That could be easier. Like any exercise that you want to know the solution. Okay, CRT tree. CRT tree is I want to leave it to the end. So before CRT tree, got any other candidates? I think CRT tree is the hardest exercise that I put out. Modulo 4. Okay, maybe I'll talk about Modulo 4. So Modulo 4 is basically this thing, which you have that, you have, okay, so if you can check that this is a prime number and this is indeed a prime number, and this is the prime minus 1 with the factorial operation. So the factorial operation basically means that you just multiply things from 1 to n. So x factorial is just 1 multiplied by 2 multiplied by 3 multiplied by n. So what is the solution of this? And if you try to compute this, you probably will not be able to like finish in time because this is just too much to compute. So you have to work out some math here. And yeah, okay. Let me show the solution for this. Give me share my screen. Okay, so the claim that we have here is that given prime, we have p minus 1 to the factorial is equivalent to 1 and negative 1 mod p. So this is we call it Wilson theorem. So anyone want to guess why is this the case? Or like, do you have like why would this be true? So the idea that we have here, so a hint here is that x inverse, the inverse of x inverse is x, right? So when we have 1 multiplied by 2, multiplied by 3, multiplied by so on until p minus 2, until p minus 1. Let's look at 2, okay. So what is 2 inverse? 2 inverse is some number here, right? Like we know that, okay, we don't know exactly what 2 inverse is, but we know that 2 inverse is maybe some I here. So some I here is 2 inverse. So when we multiply all this, when we multiply 2 and I together, we will get 1. So okay, basically these two things will cancel out, right? So this thing and this thing will cancel out. Because 2 multiplied by 2 inverse, which is one of the numbers between 1 and p minus 1, then these two things will cancel out. So 3 will also cancel out with something else. So 3 will cancel out with something. I don't know what, but it will basically cancel out with something. So everything will cancel out with something. But there's a catch, okay? So here we need to assume that x inverse is not equals to x. So if x inverse is not equals to x, then we can say that, oh, when you multiply this, then this thing and this thing will cancel out with each other. But when we do modulo p, we have something which x inverse is equals to x. And this x is exactly negative 1. So negative 1 inverse is negative 1. Because negative 1 multiplied by negative 1 is 1. So we cancel out all the things, right? We only left with one number, which is p minus 1. And p minus 1 is congruent to -1 of p. Which is why when you, yeah, so we prove this. Actually, this thing might not be very useful, just ignore that. So is Wilson theorems important? I think it was used in some, it can be used to prove some other interesting thing. I think so. I think it can be used to prove some other things, but yeah, the exact usage of that, I'm not very sure. I just know that this is a number theory fact. Yeah, maybe you can use it in some permutations, factorial, you related to that. But you usually don't do permutation modulo P. So, perhaps you can use it to prove some facts about like NCR or something like that. Okay. Okay, so there's also one, like some interesting things I want to talk about on complexity. So I show back on this one. I think you all can see. Can you all see my screen, right? You can see, right? Okay. You can see this. I'm not sure whether you are seeing the back screen or not. Okay. Never mind. Just let me stop the share first. Okay. So I want to talk about complexity 9. So this is a rather complicated thing. Okay. Oh, maybe I'll talk about complexity. Wait, let me pick. Yeah, I'll talk about complexity 9, and then complexity 7. Complexity 7 is interesting, but yeah. Okay, I'll talk about complexity 2, complexity 7, and complexity 9. Okay. So let me reshare my screen. So for complexity 2, we were solving this question. If n is 0, return 0, and then return n plus fn minus 1 plus fn minus 1. Okay, I'm not sure whether you have learned this before, but usually if we encounter like recursive sort of like function, right? We can write the function Tn. So we suppose Tn is the time that is required to run this function Fn. Then Tn, okay, so Tn is the time to run function Fn. So because in function Fn, we call Fn minus 1 and Fn minus 1 twice. So Tn can also be rewritten as O1. So the O1 is the complexity that I just do addition plus 2. Okay, not 2, but plus T, yeah, actually plus 2. Tn minus 1 plus Tn minus 1. So because Tn is the time to run function Fn, so Tn minus 1 is the time to run function Fn minus 1. So we have this recursive equation to calculate the time complexity of this. And an easy way to like analyze this is that you can have that. Okay, so you can draw out a tree. So at first you have n, right? And then you branch out to n minus 1, n minus 1. And then you branch out to n minus 2, n minus 2. And so on. And then at the very end, you get 0. Right? Because when you do 0, you just return 0, right? So you don't do the recursion in the end. So you also have t0 is equal to 0. So you sub this function in, sub this function in, sub this function in, then you get this what we call as a recursion tree. Basically, like each of the branch, right? So in each branch, right, it takes out O1 time. So this takes O1 time, this takes O1 time. Now, the time complexity of this algorithm is the sum of all the nodes in the tree. So Tn is equals to the number of nodes in the recursion tree. So now the question is, how many nodes do we have in this tree? Any guesses? I'm saying that yeah, you can, yeah. I actually asking for a more exact, like a bound, like how many are there? Like in terms of n, not just like 8 or 7. Yeah, 2 to the power of n. Why is it 2 to the power of n? Because you see, right, at first we have 1 node, and then the second branch we have 2. Then because each of the branch we multiply by 2 again, so this one we have 4, and then the next one we have 8, next one we have 16, and so on. So the height of the tree is n. So n is the height of the tree. And then because in each step we increment in each step we basically multiply by 2 again. So this is an exponential growth. So the total number of nodes we have is 1 plus 2 plus 4 plus 8 until 2 to the power of n. So do you know what this is? This is just 2 to the power of n plus 1 minus 1. Which is why we have that the time complexity is O to the power of n. Why is the sum of 1 plus 2 plus 4 plus 8 until so on is 2 to the power of n minus 1, n plus 1 minus 1? It's because we can think of this in terms of binary, right? So 1 is first bit, 2 is second bit, 3 is third bit, and so on. So I add all this together. Is basically, if you represent in binary sequence, it's just n ones. You are just n ones in terms of binary. And what is this? This is just 1 0 0 0 0 0 0 0 minus 1. So which is why this is 2 to the power of n plus 1 minus 1. Okay, so any questions on this? Okay, great. So then now I'll talk about complexity 9. Okay, I think complexity 9 is more interesting, and I don't really have much. Okay, maybe just talk about complexity 7 first. Okay, so complexity 7 is Fn, and then we have n is equals to integer n, and then if n is smaller than 2, then 0, or else you return n plus fn to the 0.5. Okay. So what is the time complexity of this? Okay, we can write down our equation, right? So our equation is Tn is equals to O1 plus T square root of n. So the three that we can get is, first one, we have like n, and then we get square root of n, and then we get square root of n, and then we get square root of n, until we become maybe like something like 2. So in each of the node, right, this is O1. So this is O1, this is O1, this is O1, and this is O1. So now the question is, how many nodes are there? First, you need to analyze the height. What is the height? Actually, the height is just equals the number of nodes, right? Because it's just like one straight line. So what is the length of this? N to the power of 0.5k. Are you sure about that? You see, right? So like, I decrease much faster than, okay, like for example, originally I was like 100, and then I square root of n, this become 10. Square root of this will become like 3 point something something. It decreased a lot quicker than you expect, because you are taking square roots and square roots and square root and square root. So okay, so the first, okay, so you're asking the question that x to the power of, okay, so x to the power of square root is this, right? Actually, you might be right. Okay, yeah. And then you take square root again, so this will become okay, so okay. Right, you might be right. So this is n to the 1 over 2, and then this is n to the 1 over 4. X to the 1 over 8. So you're asking, what is k given this? Yeah, you're right. Sorry. Yeah, you're right. So what is k? How many times you need to perform this operation until you get that this is equals to 2? Log n, log n is not correct, right? Why? Because if you think about it, right, if you do Tn is equals to O1 plus Tn divided by 2, then this is n divides by 2, n divides by 4, and n until n divides by 2 to the power of k. This, the height of this is log n. So now you are not doing division, right? You are doing square root. So you should be much slower, shorter than log n. Yeah, it needs to be less than 2, but that is just a very thing. Yeah, that is just like technical detail. Basically, I'm just asking, like, you want it to be small enough. Like how many times you need to do it until that it is small enough. Actually, no, this is not 2k. I think, yeah, this is 2 to the power of k. This is 2 to the power of k. This is not 2k. Sorry for the mistake. So to solve this, right, you can just take log on both sides. Okay, so if you take log on both sides, then this will become log of this thing, then log of 2. Then you put this down, this will become 2k, log of x, log of 2. And then you get that log of x. I don't have enough space. Okay, maybe I'll write this up here. Just write this up here. And then I erase this. Okay. So I multiply this over. Let's just assume that we are doing log 2, right? Let's just assume that we're doing log 2. So this is equal to 1. So log of x is equal to 2 to the power of k. Log 2, which is equal to 1. So what does this mean? You again take log on both sides, then you get that k is equals to log x. So the height of the tree is log x. Therefore, we have that Tn is O log n. Is this clear? So another way to think about this is like you can represent things in binary. So if you think about like if you represent a number, right? Let's say if you represent a number in binary, then if you take square root, right, it will decrease the binary representation by 1. Right? So like if you square a binary number, then one of the like the length will be decreased by 1. Actually, is it by 1? Right? I think it's by, sorry, it decreased by half. Yeah, it decreased the length of the binary sequence by half. So because the binary length is log n, then you decrease this by half every time. Then you can also get the same result that Tn is equal to log n. Okay, yeah. So any questions? So the last one is, okay, I think the last one I probably will not have enough time to talk about it because it's also quite complicated. But I want to state a fact. Log of n factorial. What is this? So O log of n factorial is O1 times 2 times 3 and so on until times n, right? So this sequence is less, this thing is less than or equals to, I just change everything to n. So what is this? This is just equals to n to the power of n. And then n to the power of n is n log n. So so log n factorial is O n log n. What else do I want to say? Yeah, I think that's okay. So, oh wait, yeah, right. Before, okay. So now maybe I should talk about CRT tree. Okay, so CRT tree asks the question that we have two equations. I'll write it in another place. X plus y to the power of 3 plus 3 let's say this is congruent to 0 modulo of prime number p. And then x squared plus y minus 10 is congruent to 0 modulo q. So now the question is, I want to find fx, y, such that this thing fulfills such that this thing modulo p times q fulfill both of the equations. So basically, if I have x fx y, I do remainder operation with p, then this should give me x plus y plus 3. And if I do on q, this should give me x squared plus y minus 10. Then then the question is how do we find fxy? So this is sort of like solving CRT with like unknowns inside. The way to do it is surprisingly not too difficult. Yeah, you can replace with a new variable first. So actually replacing with a new variable is just like a way of saying things, but in fact you don't really need to do that. So how do you do it? You let z to be equal to 0. So then you get that x plus y cubed plus 3 is congruent to, maybe I write in another direction. Z is congruent to x plus y cubed plus 3 modulo p. Z is congruent to x squared plus y minus 10 modulo q. Then you just do CRT to get something modulo PQ. So perform CRT. It's just the same thing, like you just like do all the things that how CRT usually works. Like it's exactly the same sequence of things. And then you perform CRT, and then you know that Z is equals to 0. So this is just your equation. And this is exactly fx1. You don't even need to use Z. Like you can just like put everything aside, and then all the things are 0 on that side. You just put Z is equals to 0, and then that will solve, give you the solution. Okay, so David, can you understand this? Yeah, so I think that is all for the sharing. And then thank you for coming for 5 parts. So the notes will still be available. If you want to refer that, you can do it. And then so I think the challenge, okay, so the competition is still going on. Like if you finish all the exercises, so the first place has already been claimed. So if you finish 2nd, 3rd, 4th, and 5th place, you will still get prizes. And I believe 2nd place will get shirt, right? The M53 shirt. Oh, you'll be adding on the prices. Okay, yeah. So I think, okay, yeah. Oh, I forgot to do one thing, which is to which is to okay, Yeah, I forgot to do one thing. Okay, which is discuss the solution for RSA 0 and RSA 0.5. So RSA 0 is if you download it, right? Okay, maybe I'll just share my whole screen. So for RSA 0, you are given P, so you just find Q and then you can solve it. You are given P already, so P is just n divide P, then you can just solve. That is just the solution for RSA. And RSA 0 is just trying to test your understanding on RSA. This is your RSA exercise. So for RSA 0.5, you have slightly more complicated situation, which you have T1 and T2. So you have given two things. So if instead of giving you P directly, I'm giving you P plus Q to the power of E n and P minus Q to the power of E n. So how do we do this? And yeah, so the trick is to do binomial expansion. Expansion. So P plus Q to the power of E is just yeah, this whole thing. And then basically all the middle terms cancel out. So you have that P plus Q to the power of E is equal to this. And then P minus Q to the power of E is equal to this. This is this, and this is. And so yeah, you basically already have these two. Then you just add them together. Then you get 2 P to the power of E. Then you can just use GCD to find back P. GCD with n to find back P. So the trick here is to do binomial expansion. And then all the middle terms cancel out. Okay. Then I think cube is also interesting. Yeah, so cube is just that you want to calculate this thing, which is n raised to the 2 to the power of 100 and P. So you know that you can simplify this one with the theorems that we have learned just now. This is, you can just use Fermat's-Little theorem to simplify this. So this is also pretty easy. And then you can calculate C. And actually no, yeah, this is not that. Okay, this is not a simplification. Okay, this requires a little bit of trick. So yeah, you have to basically you want to find D such that C to the power of D. Yeah. You see the Copilot already complete all the things for me. Yeah. So C here is what? C is m to the power of 2 times 100. Right? So this thing is just D. So you want to find D such that this thing holds. So what can you do? Like just now, I already given an example of this also. Okay, yeah. So basically, the exercises are all very doable, and then the beginners one are all very doable. Okay. I think yeah. So I think that would be all for the sharing. And Vihan says that we have fourth and fifth place removed, so it's just first to 3. And then 2 more set and share of sticker will be converted to radar competition price. Okay, yeah. Okay, yeah. So I think we'll make an announcement on that. Maybe can I select some questions? I don't want like I think there are some questions that are more interesting than others. So I want to select the write-up competition challenge. I select the challenge. Okay. Yeah, so that's all. Thank you. Bye bye.